Hey everyone, welcome to Janan's Projects. So today we will go through DAN plus unilateral model. We will be taking CWRU as our dataset since it is considered as benchmark for considering the fault diagnosis. We will be going through data preparation, then data processing using FFT. Then we will be building our own model, a DAN unilateral model, and then finally we will be training. Okay, we will be training using our custom gradients, and finally we will see accuracy for all the 16 cases. So let's get started.
By importing all the necessary libraries. Okay, so basically we need SciPy, Globe, NumPy, and TensorFlow, and Matplotlib for plotting graphs. Okay. After that, we will be installing one library, Keras utility, which will help us to uh, plot architecture of the model. After that, we are downloading the dataset. We are using GDAN for downloading dataset from Google Drives. Okay, so this is its unique identity. After that, we are unzipping the dataset and making one direct. Sure. We are running this to mount GPU is available for our TensorFlow library such that our topics can be a little bit faster. So next we move into data preparation. Here we have three functions. The first one is get CWRU list, the second is CWRU data, and the final one is data generator. Okay. So step by step, this will pair the data generator to get all the data sets at once. So first one is the get CWRU list. By get CWRU list function retrieves the file part of all the CWRU data set based on the load yeah, based on the load and the percentage which needs to be loaded. For 10%, it will only load one of the data set. For 20, it will load two, and for 50, it will load five, and same for 100 or 4, it will load all the 10 files. Yeah. And finally, it returns them if they load. After that, we will go for the CWRU data. So the input for this one is load percentage truncation variety. So basically, if we truncate the data which we received to 1,20,000, because some data sets are little bit longer while the others are shorter. So we need to have a standard size for all of them. That's why we are using that. After that, we are performing a segmentation. For that, we are using the length of 1024. And finally, we are using a sample size. Actually, we are not using this. Yeah. And for shuffling, we are repeating first, but we can set it to group. While the shuffling is, it will shuffle the data set, and we will get a slight different variation in the accuracy of the model, because each time the data set is somewhat different. Yeah. So yeah, first we get all the file directives which we need to fetch. After that, we are gonna have uh, data data and labels for the, you can treat this as y and treat this as x. So for the same, we are creating the to list for the x and y, our data and the labels. Okay. And then we will convert this into numpy arrays. And finally, we will convert them into data sets. Okay. So first focus on CWRU data. So after it, we are loading the data set. Like all the files are in MATLAB format only. So that's why we are loading them first. We are loading them first. Okay. After loading the data set, we truncate the data set to 12,000, 1,20,000. Yep. Okay. And then we are gonna segment it for 0 to 4. Such that the length of each segment is 1024. Then they are converted into multiples. The data is converted into multiple segment of 1024. After that, we are gonna apply linear transformation for converting the time domain function into a frequency domain function. And we are gonna finally append all the transformation which we get in our data set into output. I already told that we made one list name as art, which will contain all the data for our query. Okay, you can consider them as X. And we also get labels. So label append the labels where we are append all the labels for all the data sets into labels list. Then we are gonna augment all the where we are gonna augment the our data, like the augment our x and y's. So here's 4%, like we are gonna calculate this. Okay. So augmentation percent determines the augmentation factors. For example, if the percentage is 20, the data needs to be repeated 5 times to get a sample of product 2000. So the data, this basically means that the data segmentation, like for hits out, and the labels are duplicated 5 times such that it can augment the data set. Okay. So why we need to increase, why are we multiplying? The multiplication increases the size of the data set, simulating a larger data set. This is very useful in training machine learning models, especially while our data set is limited, or for other thing, like basically for when our data set is limited. Okay. So for getting the augmentation factor, you can guess, like if the 20% of 2000, like we have a total sample size of 2000. So 20% of 2000 is 400, and 400 multiplied by 5 both should be 2000. That's right. Okay. We are gonna, like, we need to achieve a size of 2000. That's what we are multiplying. The same goes for 10%. So for getting 2000, so we have to multiply it for, and same goes for 550 also. Like for achieving a full sample size of 2000, we need 2 times of 50% to get full sample. That is for same for the 10% also. Okay. So here we are having our support before we are converting them into our data. Okay. So the shuffling is used basically for shuffling is used here basically to suffer out all the like the labels and the x values. Okay. This is necessary to bring some variation into our data set, and if the suffer is set true, then it will suffer. Finally, we are converting our labels into categorical data. This categorical format is often done in machine learning when dealing in multi-class classification problems, or two-category function converts the class selector to binary class matrix in zeros and ones, such that the classification is more successful. Then finally, we are outputting the data, which are outs, and the labels, which are y's, x and y, in the form of the NumPy arrays. So finally, we arrive into our brief function code. So the data generator, the data gen function is responsible for generating all the batches of data for training and testing domain DAN model. Okay. It handles data preparation, batching, supply, support, source and target data sets. Okay. So here you can see we have put our suffer into true. Okay. So here we will be submitting the data set also. So the first gear which we are gonna get is retrieve the source data and source labels using this line. Okay, so this retrieval function I have already explained you about, like how we are gonna retrieve everything from CWRU data function, and this is getting all the list from error. So I guess you understand how the function works. After that, we are gonna get our target data and target labels for training using the specified percentage of the input. Like we can input the batch size is used for generators, and the percentage which needs to be which we need to get using target and labels. Okay. And finally, we are gonna get target data full labels and target data and target labels for testing purpose. Okay. After that, we are gonna utilize the TensorFlow dataset object to convert our NumPy arrays for source and data into TensorFlow dataset objects. This conversion utilizes the TensorFlow data pipeline functionality to load the data and reprocess them more efficiently and save some memory also. Okay. After that, we are gonna generate the data generators such that we can limit, like we can divide the whole data into various batches. Okay. I guess you know what data generators are. Data generators are specific kind of function that returns an iterator which produces sequence of values when it repeated over and over again. They are useful. Basically, they are useful when we are writing a large sequence of values like we have already augmented. So it's kind of like large. Okay. And they're always using data machine learning models. So they are essentially used for generating the batches of the dataset, which can later be used for our training and testing purposes. Okay. So the source data generator full dispatches the source data for training with specified batch size. After that, you're gonna have target data generator full, data generator dot batch. Uh, These batches the target data for training with specified batch sizes. Then we have source data generator half and the target data generator half. Okay, so this batches the source and the target data for training with our the specified batch. Like we are for hours we are using 64 batches because our machine can support that. Okay. Uh, and this the half datasets are used for the feature extractor and discriminator values, which we will see later in our model. Okay. After that, we are gonna use something as target data generator test to with full. Okay. And batch size of one. This is essentially used for validation and testing purposes. The batch size of one ensures that each test sample is evaluated independently and works individually. So this is the whole data preparation part. I guess you understood this one. So this is this I have written only to test whether CWRU list is working or not. Okay. So if we have successfully downloaded the dataset and successfully got our dataset here, so this should output to a 5 dataset directly. Okay. That's it. Okay. So that is our whole data preparation part. So we will next move into pre-related. So let's start with the pre-related first. So what does the pre-related does? So what is the basic thing which it does? So it is integrated into the model. It will pass the inputs on. It will pass the input engine where we are happening to be in forward pass, but it will integrate during the backward pass. This is the basic function of the flip learning. Okay, so now let's see how it is doing. So first you are gonna define the function which is reverse grad function. Reverse the gradient of. So this is a custom gradient operator along with which is defined along with the conceptual decorator. You can ask what the decorators are. So the decorator are used in Python to convert any function and Python function into the graph function. Okay, so what are the graph functions and what is so in Python or in TensorFlow, we have two kind of execution modes. The first one is the eager mode and the second one is the graph mode. Eager mode is a standard interactive get-to-run code. Every time you call a function, it is executed as it is. So this is the eager mode, but the graph mode is somewhat different. Graph mode creates a computation graph before it executes the function, and this computation graph allows the TensorFlow to simplify the computation and find opportunity for enhancing the performance of the model. So what we are doing here, we are doing something as known as function transformation. So we are taking the function and decorating it with TensorFlow decorator, which is TensorFlow custom integrated. Okay. Now this function will be executed in two steps. The first will be in the eager mode where the TensorFlow executes the Python code for the function, and the second will be the computation graph mode. After that, we are gonna copy the tensor X, which is executed in the getting the model execution part, model training part. Okay. So this plan basically creates a tensor Y, which is identical to input tensor X. So why we are doing this? So this function is used to ensure that the Y is treated as a new tensor, even though it was the same value as X, and it can undergo differences during the custom during the training part. Okay. After that, we are gonna define another function which is custom grade. This function defines custom grade for the operation, which when the backward pass of the gradient occurs or computation occurs, Instead of propagating the gradient directly, it negates the values of the ty, and then it allows to get transmitted. So this means that during back propagation, the direction of the gradient is fixed. Okay, and then we are gonna return our values y and the custom grid. Um, y is this during the forward pass, which is the same as the x, but the custom there was specify how to compute the custom gradients. Yeah. Like you should negate or what. After that, we are gonna define one class, which is a grade reverse class. Okay. As you can see here, this class is a custom care. This is basically a custom class here that uses the grade the reverse function, which we have already defined here. First, 18 is like this. The constructor simply calls the layer by calling the parent class, which is TensorFlow keras layer. Okay. After that, we are gonna feed our class into forward pass. The forms in the class method, the call method, the call method defines the forward pass of the layer when the layer is applied to tensor x. It calls the get reverse function. It calls the get reverse function. On x, this means that all the output of the forward pass is same as the x. Like for the forward pass, we are gonna return the y values. But for the backward propagation, we are gonna reverse the gradients which we obtained by reverse that function. Okay, so finally we are gonna build an instance of the reverse gear, which is make rate, which you can see here. We are gonna use 0 in our model. So yeah, this is the whole custom gradient part, which you gonna understand. So I hope you will get this way. But not the things we'll get it every time. So out of the flip gradient, we should move into our model connection part. Okay, so our model consists of feature, extractor, classifier, and discriminator. These are the three main part of our model. So first, let's see what is our model and what these three things are. So the model helps in domain adaptation by simultaneously training the classifier on the source domain and the discriminator to make feature representation domain invariant. The gradient reversal layer, which I have already put here in the flip gradient part. The what is it? Yeah. So the gradient reversal layer ensures that the feature extractor learns the produce features that are different between source and target domains. Okay. So, and what does the feature extractor and classifier discriminate? All this is. So the feature extractor accepts the input data using the convolutional layers and the dropout layers for convolutional and dropout layer. Then we have something as classifier. Classifier predicts the class label for the extracted features. Finally, we have something as discriminator. Discriminator predicts the domain, source, or target of the feature with gradient reversal to encourage domain the invariant learning feature learning. Okay. Then we will have something as model, which combines the feature extractor, classifier, distributor to single model that outputs both the class and the domain prediction. Then we have something as feature extractor, which is same as the feature extractor which we have defined here, but is for slightly different uses, which I will tell you later. Okay. So let's first move on with the feature extractor part. In feature extractor part, we have three convolutional layers, the first one, the second one, and the third one here. So each convolutional layers has 10 filters and 3 kernels. These are the name of each layer, fcon1, fcon2, fcon3, with the and the first input layer has the shape of inputs are shape of 512 by 1. So these convolutional layers are responsible for extracting the local feature from the input data. After that, we have something as dropout layers, which is set to 50% or you can say 0.5%, which randomly drops 50% of the correction during the training such that we can prevent the overfitting of our model. Okay. After that, after convolution and dropout layer for feature extraction, we have something as flattening. The flattening is used to flatten all the outputs which we have got from our final convolutional layer into a 1D layer, 1D vector, using this final flattening layer. Okay, the name for the flatting layer is flat, feature flatter. After that, we are storing every feature which we have got from the feature extractor part into feature extract. Okay, so it is connected to our dense layer of the 6 with a sigmoid application function, and is a final feature extractor layer for the feature extractor function. Okay, I guess you need to have some basic knowledge of the deep machine learning, and you will be good to go. That's it. Okay, nothing fancy. Then we have something as classifier and the discriminator. Okay, so the features from the feature extractor is then given to our classifiers and our discriminators. So what does the classifier does? The classifier has a dense layer of 256 units, and the activation function is our classifier. This is RELU. Okay, RELU with the name of the first dense layer is of classifier MC1. Here the input function from the above which we have got, and here's it. So about this. Yeah, and then we are using a dropout layer of 0.5 to prevent the overfitting. Then we are finally giving the prediction of the class into 10 different units, like because we have 10 units in each. You can see here also clear. We have 10 different units when we have. So you don't need to confuse it whether if we are using portfolio or how. Because basically we are using that for targets now. So this, so our feature extractor classifier is complete, and we will proceed on with the discriminator part. Okay. So the discriminator part has fully connected layers with two dense layers of 124 unit and a RELU activation function, which finally gives off two classifications like the two units, because we are assuming there's a binary domain classification of source at the domain and the source and the targets. There's a binary classification domain. That's why we are using the two here. Okay. So finally, we have something as a Daniel model, which combines all the three layers here, and finally makes a model along with a flip gradient part. Okay, so first we are inputting the model using the input set, which is 500 and 512 by 1, which you can see also, which we have okay. After that, we are gonna have something as feature extractor, which you extract the feature from the input data. Then we are gonna give it to our classifier. After classifier, we are gonna have something as flip gradient part. So flip gradient flips the gradient for discriminator, which is then input into our discriminator, and then we are gonna output something as we are gonna output something as model or something as Keras model that outputs both class prediction and the domain predictions. Okay, and then we are gonna return that model to our user. Here we are gonna input the shape as 512 by 1 and then compile the models. This is the feature extractor which is used. This is used as a source domain feature extractor. Only that's why I have defined it differently here. Okay. After that, we are gonna compile the two models using the feature extractor from the model world for the source domain, and then we are gonna have something as model which is our main model with the DAN model with input set. And then we have something as optimizer using we are using add-ons optimizer with a learning rate of 0.01. Okay, that we have something as model architecture. Remember, initially I have told you that we are gonna utilize Keras utility. So here is the utility of the Keras utility. So basically, we are gonna plot the architecture of our model. So here you can see the names of the layers also, the F1 layer, the input layer. So these are the after the feature extractor part. This is the feature extractor part which you are seeing here. After the feature extractor part, you can see the last layer was 256 on the okay. So the dense layer. After that, we are gonna something as the discriminator and the classifier. Here are the classifier with all the dense layer, dropout layer, dense dropout, and the dense layer. The final dense layer are the 10 units, and dense layer 6 unit. That for discriminator, we have something that's reverse layer of 256, then dense layer of 104, and finally a dense layer of two outputs. So this is the whole model comparison. And so this is the model architecture there. We have done our model architecture. After that, we are gonna move into training session. Training session for that, let's and this works. Okay, so that we have something to show to compile the model better. Oh, well, yeah. So this is our training session, our training function. It is used to train it is used to train a DAN for a specified number of the epochs, okay, which we gain in some data. It incorporates source domain classification, domain discriminator, consistency loss from the classifier, and to achieve the domain adaptation. The function updates the model parameter using the gradient descent and the deep values and evaluates the model based on the validation set. Okay. Okay, so inside is the most important concept is for the gradient, which I will explain. So first we are gonna initialize the list to track the accuracy training loss validation loss for each epoch. I guess I have written it twice here. Okay, no problem with this. Okay. And this functions gives the rates of like for all the epochs. If we will set for 200, then it will for this is a iterative that. So simple. This prints the epoch numbers, which you are seeing here. This is printed by the first one only. Okay. So yeah. Then they are initializing all the list which we are gonna use to keep track of our accuracies and loss for various training and validation purposes. After that, we will initialize our main training function and we training programs. So the first one, here, it iterates over the batches of the source and the target domain using the data generator which we have earlier initialized, as you will. Okay, so here we are taking the source data generator, and this is the source and the target data using the half of this for the distributor, and this one is for the classifier for each system. After that, we are gonna initialize something which is known as gradient depth. The gradient depth is used to record the operation for the automatic differentiations. So basically, this is a vast topic, but I will try to explain it first. And okay. So basically, what is a gradient depth used for? Is particularly useful when defining our custom training group, custom gradient, and custom layers. In model practice, what you see, so we can directly write. We don't need to write all this first. We just can write simple line of course. So like after compiling which are directly the training source, we just need to name the type of loss and it will be working. Okay, no, don't need to class what's it? We don't need to mention all this everything here. Okay, but still, since this is a custom layer and custom model with customers, we are gonna use something as pre-updated. So pre-updated tape is a powerful feature which is level 8 TensorFlow for automatic differentiation used to compute the gradient of the composition with respect to the input of x and y's. Okay, in TensorFlow 1 also we have something as TensorFlow variables and graph functions, which are similar to this one. Okay. TensorFlow requires relevant operations, like I have already told you, which are executed inside the context while training the models. So how it works, like what we do and how it works. So recording operations, it means that when we perform operation inside TF gradient depth, TensorFlow records them into something as tape, which we will see later. Yeah, so it records them into tape. Then this tape keeps tracks of each operation and each tenses that goes through it. Like updating the accuracy needs to be updated. So how it is getting updated automatically? So here we are using the gradient or the gradient table, which is used in our model. After that, we have something else, automatic differentiation, which I initially do. Like once the operations are recorded, we can use something as tape gradient. Tape gradient method to calculate the gradient of the recorded computation with respect to the loss value model, loss value, which is used to evaluate the training weights of the model. Okay. So after initializing the gradient depth, we are gonna have something else. Classify loss for the class, like this line is used for the classification classifier and its loss. Okay. So basically here we are gonna have something as forward pass with the source domain data, source F. which is used for the classification. We get the classification output and compute the loss values, which is calculated using the cross entropy function, cross entropy loss methodologies. Okay. So here we are getting one loss, which is classifier loss. This is the same thing which we the TensorFlow one has compiled, but only doing something different. But this is the main thing. Okay, like they are also calculating classifier loss, discriminator loss, and consistency loss, and we have used all the same thing also. Okay. So first one is the classification with the loss. So this is the classification for the loss. So, after that we are calculating something as consistency loss. So yeah, we are gonna extract it using the feature as well, and then we are gonna extract them using the model as here we are gonna extract the with model as two, and then we are gonna extract model as well. Yeah, remember I have defined one simple model for the feature extraction. This is the same model which I have defined here. After that, we are gonna extract the feature map from the intermediate layers of the S2 and the S1. Uh, after the after extracting the features, we are gonna calculate the consistency loss here, which is which is the mean absolute difference between the feature maps of the S1 and the S2 features. Okay. After that, we are gonna do something as discriminator loss. Okay, while training how much is loss in the discriminator part. So we are gonna see that one. So then for calculating the discriminator loss, we are gonna first quantity. We are gonna first join the source and the target domain data. Like I have told you that we are gonna have something as half data from the source and half data from the target initially while preparing it as a data. So here we are using there pairing them and using them for our classes for our discriminator. Okay. After that, we are gonna create domain labels. Where source label is labeled as 01 and target domain are labeled as 0. So source domain are labeled as 10 and target domains are labeled as 01. Okay, for the half the base sizes. So we are okay. Because initially all the data are from sources, so we are gonna have something as 01 or half the base size because only half is available. As you can see here, this is source half and then we have target half. So suppose here. So this is stacking. You can see something we have something as a V stacking and we have also something as stacking. So you can see what they are. So after concatenating, we are gonna have something as stacking. Okay. And we are gonna create the domain labels. So here we have created our data and label for the discriminators. Yeah, saying the half of the base size like 32 is gonna be our target. Okay, so I hope you got how we got this data and labels. After that, we are gonna have something as loss and classifier training. So here they are gonna have some domain output of the discrimination loss. So this is for the discriminator. This one for the classifier, and this one is for calculating the consistency loss. Okay. After that, we are having something as regularizers for our TensorFlow. So we don't need to define differently, but this is we are putting from TensorFlow 1 to 2. We are defining them. This is the lambda. Okay, so the total loss value which we have got is addition of all the three values, the classified loss, the distributed loss, and the mass about consistency. Okay. After that, we are like I have already explained what this is. We are gonna apply the optimizers to our model. If the model to they're gonna optimize, then we are gonna append the accuracies. Usually, we are calculating the categorical accuracy. Okay, and where we are gonna append for updating the training matrix. Then we are gonna append the training loss, and then finally we are gonna append the progress bar. Yeah, so this is the progress bar, and these are the accuracy matrix which we are gonna append and update that. After that, we have something for the validation. For validations, we are gonna initialize the dish. Okay. Then after training the model, we are initializing the list, grab the validation labels output classes, and you are gonna iterate over the validation data to get all the prediction and compute the validation loss. Finally, we are gonna calculate the accuracy of the predictions and accuracy of the predictions and the loss of the predictions. So this is the final validation part. After that, we are gonna print the training test and testing loss and accuracies. And we are gonna fit them into one. So yeah, this is the training session. After that, these are the 4 lists which are which I have created to accumulate all the final accuracy. These are the lists which are used to append the final accuracy loss for all the training and validation data. Okay, so this is used here. Yeah, this is just output this table. Okay, so as to accumulate the accumulators for the training accuracy and the loss are outputting there. Did I? Okay. So after that, we are just training the models. These are the training the models. This is training model for source is equal to 1 and target 0, 1, 2, 3. Like you can see, source is 1 and target 0, 1, 2, 3, 1, 0, 1. And then we are going to have something as 2 and 3. Okay. So same goes for source and target 0, 1, 2, 3. Then 2 and target 1, 3. And 3 for target 1, 3. Okay. So these are the things which we have. After that, we are gonna give a something in the form of a table. This is a table which we have created using function element. After that, we are logging it like we are giving the log file which is asked along with the data. So yeah, this is the full DAN model. I hope you understand. Thank you.